Welcome to the third lesson of Module 2, Strategies and Technologies for Energy Efficiency in Data Centers. In this final lesson of the module, we move to a broader perspective, the infrastructure and architectural design choices that shape the long-term energy footprint of a data center. Infrastructure design plays a foundational role in the overall energy performance of a data center. Decisions that taken during the planning and construction phases, such as site location, building orientation, envelope materials, and power distribution, have long-lasting effects on both operational costs and environmental impact. Unlike IT or cooling systems, which can be upgraded frequently, infrastructure design choices often persist for decades. These make them especially important for sustainable development. One of the first considerations is site location and climate context. Data centers situated in cooler regions can take advantage of free cooling for much of the year, reducing reliance on mechanical chillers. Conversely, facilities in hot and humid climates must invest in more robust cooling infrastructure, increasing both capital and operational costs. Orientation and shading of the building also matter. Limiting solar gain through proper design can reduce cooling load significantly. In addition, site selection must account for risks such as natural disaster, political stability, and grid reliability. For example, locating near renewable energy resources or stable electricity supply can support long-term efficiency and resilience. The building envelope, consisting of the materials and structures separating internal from external environments, has a direct impact on the thermal performance. High-performance insulation, reflective roofing, and low emissivity windows help reduce heat transfer, minimizing cooling demand. Airflow management can be integrated into the building layout, ensuring efficient distribution of air conditioning. Power distribution design is another critical area. Electricity losses occur at every stage of conversion and transmission. Traditional double conversion UPS systems operate at 92–96% efficiency, meaning several percentage points of energy are lost as heat. Similarly, minimizing cable lengths using efficient transformers and designing compact layouts all help cut transmission losses. Though this may seem like incremental improvements, at the larger scale of a data center, they translate into significant energy savings and reduced cooling requirements. Integration with renewable energy is becoming increasingly important as operators aim for carbon neutrality. On-site solar photovoltaic panels, wind turbines, or biomass plants can supply a portion of the facility's demand. Coupling renewables with battery storage enhances flexibility, enabling load shifting and peak shaving. For example, stored energy can be dispatched during high-demand periods to reduce reliance on fossil fuel generations, lowering both costs and emissions. Beyond electricity generation, heat recovery represents an opportunity. Data centers produce substantial amount of waste heat, typically vented to the atmosphere. With proper infrastructure, this heat can be captured and reused for district heating, industrial processes, or even greenhouses. Implementations in Scandinavia and parts of Europe have demonstrated the feasibility and benefits of such systems. Similarly, cogeneration and three-generation systems, where natural gas or biogas are used to produce electricity and the waste heat is captured for heating and cooling, can achieve overall system efficiency above 70%. These solutions require coordination with local infrastructures but can dramatically increase total energy productivity. Scalability and modular design are also important aspects of the sustainable infrastructure. Rather than building oversized facilities that operate underutilized for years, modular data centers allow incremental expansion in line with demand. This reduces idle infrastructures, aligns capacity with actual needs, and avoids unnecessary energy waste. Sustainability in infrastructures extends beyond energy efficiency. Water consumption is another critical factor, particularly for cooling systems in water-stressed regions. Facilities are increasingly aiming to minimize water use, either by adopting air-based or hybrid cooling systems or by integrating water recycling. The integration of digital infrastructure management tools further enhances sustainable design. Building information modeling and digital twins can be used during the design phase to simulate energy flows, cooling needs, and renewable integration. This predictive approach helps identify inefficiencies before construction, allowing for smarter investment decisions. In conclusion, infrastructure and architectural design choices set the foundation for the long-term energy efficiency and sustainability for data centers. From site selection and building envelopes to power distribution and renewable integration, these elements collectively determine the baseline performance of a facility. This concludes Module 2, Strategies and Technologies for Energy Efficiency in Data Centers. In this module, we explored how energy optimization can be pursued at multiple levels, through IT utilization strategies, through improved cooling and climate control, and through sustainable infrastructure design. Together, these strategies provide a comprehensive framework for reducing the energy footprint of data centers. In the next module, we will shift focus from physical and architectural strategies to digital solutions, exploring how monitoring systems, automation, artificial intelligence, and digital twins can dynamically optimize energy efficiency in real time.